Hi everyone, welcome back to my channel, the place where science and creativity collide. Today we're taking on an ambitious project, building a high voltage measuring device capable of safely handling voltages of thousands of volts. So what's the plan? High voltages are tricky to measure directly because most standard multimeters can't handle them. That's where a resistor voltage divider comes in. It reduces the high voltage to a lower, manageable range that's safe to measure. Let me show you the stars of today's project, resistors. And not just a few, from this pile I will be choosing top ranging values and will use them to create a high precision resistor voltage divider. The plan is to mount these resistors onto this board, carefully aligning and soldering them into a zigzag pattern, starting from the bottom right corner up to the top and returning on the next column until all the resistors are used. Ideally is to have the same value resistors everywhere, but in my case I will start by preparing the highest value resistors first and decrement each step until all the higher values are used. Alright then, let's start by placing all the resistors onto the board one by one on the same way I explained earlier. I won't lie guys, this was tedious work, so at this point I would really appreciate if you drop a subscribe to this channel if you haven't already done so. Moving on, this is how it looks like at this point. I have used a total of 136 resistors with values ranging from 10 megaohms down to 510 kiloohms. Next step is to solder all of them in series and be careful not to miss or short any of it, because any defect on such high resistance value would be extremely difficult to later troubleshoot with any measuring device. Now, after cutting it to size, next step is to solder the wires, starting with the high voltage cables at each end of the board. Next, I'm soldering the measuring wires across one of the lowest value resistor, which is 510 kiloohms. This is what we have until now, all 136 resistors soldered and ready to use. However, I first want to find a way to remove all the unnecessary metallic parts between the connections, such as to reduce the possibility of high voltage arcing between resistors. For this purpose, I will use this soldering station on the highest temperature setting, which is 450 degrees Celsius. Now we finally finished the meticulous part of this project. This is the schematic and this is the measuring formula for this divider. Alright, we've reached an exciting stage now. Our resistor divider is fully soldered and functional. But we're not stopping here. To make this device durable, insulated and safe for high voltage measurements, we're about to encase it in two protective layers: heat shrink tubing and solid wax. I've selected a heat shrink tube that fits snugly over the board while leaving room for the cables to pass through. Getting these just right takes a bit of patience. In this step, I seal one end using an iron, such as it will hold the liquid wax when pouring it over. For the wax part, I'm melting a thick candle. The whole process took about 10 minutes. In the meantime, I reinforced the seal on the bottom part with some electrical tape and filled the entire case with melted wax until it covered the board entirely. And although while pouring, some drops still managed to escape out through the bottom, after placing the entire device into cold water, in the end it still turned out to be a success. Finally, we have the finished product, and now it's time to run some tests. Because this is basically a converter, the first thing we need is to find out the converting constant of this divider. For this, we need to make some low voltage measurements using some established voltage sources that we know the value of. So in the first test, I'm measuring a divider output voltage of 19.5 millivolts out of this 31.5 volts lab bench power supply. Now we can define our constant as V output over V input. Now it's time to make a measurement of the mains voltage. In my case, I have 240 volts AC into the power socket. But before we can make a measurement, we first need to convert the voltage into DC using a full bridge rectifier such as this one that I made. The rectification process increases the voltage with the square root of 2, which in my case is 325 volts DC. Again, using the divider we just built, we are getting an output voltage of 204 millivolts, which gives us another constant which is very close to the first one we have measured using the lab bench power supply. That being said, I choose a middle value of 0.000625, which I define it as a new calculated constant of this divider. Although it's very strange because the calculated constant is way smaller than the one we found out while doing these measurements. If you know why this is happening, feel free to leave a comment. I've always wanted to measure the voltage output of this bad boy here. It is said to be rated at 2 kilovolts, but is it really? Let's find out together. First, we need to build a full bridge rectifier that can withstand the high voltages of the microwave oven transformer. So to do this, I am going to use 4 high voltage microwave oven diodes. You see, the problem with high voltage AC is that it is particularly hard to measure directly using this method, because it induces 2 more parameters in our equations called reactances, especially inductive and capacitive reactances that are variable and messes up our constant. Plus, it increases the risk of inside arcing and damaging the resistors. This is the finished bridge rectifier, and after soldering the input wires, it is time for testing with the microwave oven transformer. I'm measuring 2.04 volts DC. If we divide this output voltage by our constant, we get 3264 volts DC, which if we further divide it by the square root of 2, we are getting 2307 volts AC, which is pretty much accurate if you ask me. But anyways, another way of measuring the output voltage of this microwave oven transformer is by limiting the voltage input via an autotransformer such as this one and measuring the output voltage with a standard multimeter. Next step is to find the transformation ratio, which for this transformer is 9.5, and multiply it by the input voltage, which gives us a value in the same range over 2000 volts. But what about a flyback transformer? Let's find out. It turns out this flyback gives us an output voltage of 5.96 volts, which again we will divide it by the converter constant and give us a value of 9.5 kilovolts DC. I really hope you like this video. If you wanna see more, subscribe and see you next time. Bye bye.